there, welcome back to Common Core Algebra 2. Today's lesson is 9.3, Solving Quadratic Equations with Complex Solutions. I know this is kind of hard to read, but basically we're talking about quadratic equations that have roots that are not real numbers. All right, and basically, as we've been talking about through the rest of Unit 9, they're going to turn out to be complex numbers. All right, now we have to start looking at this thing called the discriminant. And that discriminant right here, when you see our quadratic formula, is going to be that b squared minus 4ac. All right, and we're going to start talking a little bit about that discriminant and what's called the nature of the roots a little more in lesson 4. But for today, we're going to really just take a look at using the quadratic formula and what the roots look like when they're not real roots and there are complex roots. They're going to look like complex numbers, but they're going to have sometimes radicals in there. They're going to look a little weird, so I think it's important to take a look at how to do these. All right, so this is all about the quadratic formula that's found on your reference sheet, or you can write it down. If it helps you, write the equation down first. So x is equal to negative b plus and minus the square root of b squared minus 4ac all over 2a. I'm going to remind you that the a is the coefficient in front of the quadratic term, the b is the coefficient in front of the linear term, and the c is the constant. And if it helps you, write it out. A is 1, b is negative 4, and c is positive 29. So now let's do some substituting here. And x is equal to the opposite of b. So since b is negative 4, I know my opposite of b is going to be positive 4. Plus and minus the square root of b squared. Now, when you do b squared, make sure you're putting that negative 4 in parentheses, or simply put 4, because when we square it, it's always going to become positive. Minus 4 times a times c all over 2 times a. Now, people ask me all the time, do I have to put the 1 in there? Do I have to put the 1 here next to the 4? And the answer is no, you do not have to. All right? And once you get good at this and proficient at this, you won't have to put the plus sign in front of the 4 either. All right? So in this case, x is equal to positive 4 plus and minus. And the next thing I do is I determine what my discriminant is. So I put that into my calculator, just this part right here. So I just put this into my calculator to determine what that radical is. Now in this case, when I do it, I get negative 100. All right, all over 2a, which is of course just 2. So when I look at this, I know that this is the same thing. So over here, I'm just going to show you. We have negative 100, which is the same thing as 100 times negative 1, just like when we used to split up perfect squares and what was leftovers. So the perfect square is 10, and then the radical negative 1 is our I. So we rewrite this as x equals 4 plus and minus 10i divided by 2. And then the very last step is simply to just simplify. And when we simplify, when you have this divided by 2, this is divided by 2, and this is divided by 2. So x is equal to 2 plus and minus 5i. Now, I'm going to remind you, that's 2 different roots. We have 2 minus 5i, and we have 2 plus 5i. Okay? And it says to make sure that you express your answers in simplest a plus bi form. And that's what we did. Please take a minute and look at what I did here. If something's confusing you, make a note, so when I ask you if there are any questions on this video, you can say, oh, where did you get this from? Where did you get that from? How did you go from this point to that point? All right? I want to hear those kind of questions. I wish I could make this video interactive so you could ask me. Okay, moving on to exercise 2. So here we have 2 problems. So why don't you try them on your own? I'm pretty sure you don't need my help with this. So why don't you try them on your own? I will take you through A, and then I'll put the solution up to B. Okay? Okay, here we go for A. So the first thing, I know this is a quadratic because of the x squared, and I know this has to be set equal to 0. So the first thing I'm going to do is I'm going to take this on my right-hand side, and I'm going to bring it over here to this side. So when I cancel these out, I get my 0 on this side, and here I get x squared minus 12x plus 40. Now the first thing, it will not usually tell you that you're definitely going to get complex roots here. So your first thought might be to try and factor it. But hopefully you'll realize pretty quickly that there are no two numbers that multiply to 40 that add to give me 12. So this is what's called a prime, or it actually will end up being complex. It's not factorable. Okay, so it's a non-factorable, sometimes we call it a prime quadratic, which means you have to use the quadratic formula. All right, so again, if it's helpful to you, A is equal to 1, B is equal to negative 12, C is equal to 40. And we are going to plug these in to our quadratic formula. So x is equal to the opposite of b, which is positive 12, plus and minus the square root of b squared. Now I'm just going to put, some people will even do 12 squared, not even putting the minus sign in the front, because they know when they square it, it's still going to become positive. Minus 4 times a, which is 1, times c, which is 40, all divided by 2 times a, so it's 2 times 1, which is 2. So you can do a little bit of shortcuts here and there that might help you just simplify your equation a little bit. So 12. Now notice when I say it, I say the opposite of 12, because that's how I always remember it. Because I remember if b in this case is negative 12, I know the opposite of negative 12 is positive 12. So that's the way I read it. I generally don't read it as negative 12. So we have 12 plus or minus, and once again, I'm going to put 12 squared minus 4 times 40 into my calculator, and I'm actually going to get 144 minus 160, which is minus 16, all over 2. That minus tells me I'm going to have an I in here, so I'm going to have 12 plus and minus 4I divided by 2. All right, because remember, the square root of negative 16 is the square root of 16 times the square root of negative 1, which is 4i. So now I do my final calculation here, and I get 6 plus or minus 2i. So remember what that means. X is equal to 6 minus 2i and 6 plus 2i. Right? So I want you to give B a try, so pause the video, and then I'm just going to put the answer up on the board. Okay, ready for the answer? I'm going to just slide it up a little bit, and I'm going to, bam. Okay, so here's the answer to B. So beware when you're getting over to this point. All right, just look here for a second before you start writing things down. When you get here to the square root of negative 8, pay attention that this is how we simplify that. All right, because here we're actually going to have a radical in there too. So you're going to have the square root of 4 times the square root of 1 times that negative 1, which is I. Notice how we don't put the I at the back. We put the I at the front, so that way we don't get confused whether it's under the radical or not under the radical. Okay, so that's just a notation trick to make sure that, because some people might think this, if you wrote this, you might write it as 2 radical 2i, and people won't know if that's including it or not including it. So we don't like to do that. We like to write it like this right here. All right? So if you need some clarification on that, just let me know. We can talk about that in our first 10 minutes. All right? And I think we have one more to do. Actually, we have a couple more to do. And I want to try and keep this as fast as I can. So if you need to write that down, write it down, and then meet me at exercise 3. Okay, so there's an interesting connection between the x-intercepts, or the zeros of a parabola, and the complex roots with non-zero imaginary parts. All right, so in this case, let's just do this real fast. And I'm going to do it for you so we don't have to spend an awful lot of time. But when we solve this equation right here, all right, I didn't give you a lot of room here because basically I'm just going to tell you the answers are 3 minus 2i and 3 plus 2i after I use my quadratic formula. All right, and then the next part says, B says, using your calculator, sketch the graph of the parabola. And if you do that, the parabola comes out looking something like this. And as you can see, and it says C, from your answers in part A and B, what can be said about the parabolas whose zeros are complex roots? Well, remember what a root is. It means where it crosses the x-axis, and we have nothing crossing the x-axis here. Okay, so let's not make a big fuss about this one. I just wanted to bring that to your attention. So you're going to say here, parabolas, let's use the wording from our problem. Parabolas, I can spell, parabolas whose zeros are complex roots have no x-intercepts. Okay, moving on to exercise 4. Use the discriminant of each of the following quadratics to determine whether it has x-intercepts. So what we mean by that is we're going to talk about this a little bit more in 9.4, but if you consider that discriminant part, remember what that is. It's the b squared minus 4ac. So in this case, a is 1, b is negative 3, and c is negative 10. So we get the square roots, and actually you don't even need the square root part. We're really just looking at what that b squared minus 4ac is. All right, so we get b squared, which is 9, minus 4 times a, which is 1, times 10, which is, times c, which is negative 10, and you get 9 plus 40. So does this have x-intercepts? This turns out to be 49. So I know we're going to have a perfect square here